It's my pleasure to introduce Professor Atul Srivastava. He did his master's and PhD both from IIT Kanpur in 2000 and 2006 respectively, and after his few jobs at different places including RRCat Indore, he joined IIT Bombay 2011, and after that if you see his profile, he's been very active in many places, including his academics. You might have seen him in sports or in cricket. He's front leader there, and also handling our sports activities for institute. And he has received a Swarna Jayanti fellowship in 2015, and he's since 2021 he's institute chair professor here. And a couple of his students, including he himself, when he was at IIT Kanpur, they have received the best PhD thesis award. Like at least 3 students have received in IIT Bombay, which is quite commendable from from single faculty coming to that stage. Okay, so he has been working actively in this area of optical investigations or optical measurement techniques for thermal measurements, and he'll share some of these insights to us today. Thank you.
Yeah. Thanks, Professor Gandhi. So thank you very much. Professor Khakkar was generous enough to tell me that he was the chair for this committee. So thank you very much, and the committee members and the IRCC. So this is I'm going to talk about I will be giving an overview of what activities, research activities we are involved in. Basically the title is Breaking the Barrier of 3-dimensional time resolved measurements in fluent thermal systems. These are some of the pictures that have been shown over here. These are optics based measurements. Even though the core field is fluent thermal systems, but we borrow some fundamental basic principles from physics, optics, material science, and we make use of them. And one of the highlights is that none of these systems that we are using for our studies, they have been commercially purchased. What we do, we basically procure different components, and that is where the credit goes to the students, that even though they are from mechanical engineering background, they have that kind of enthusiasm to get into basic optics and configure these setups. Sometimes it happens that a student is working in daytime and he is using that alignment, but in the night time someone else comes and he uses the same table but then reconfigures the setup so that it suits his application. So that way the students have been really devoted. And so primary motivation of the work is of course the time dependent and 3-dimensional distributions of fluid properties, flow properties and flow velocities and transported parameters. They are required in various range of applications, and this possibly explains the growing popularity of simulation tools like computational fluid dynamics, because it provides you wealth of information. However, generating such kind of voluminous data through experiments has always been challenging. This is one of the demonstrative video where you have a flame, and then if you want to measure the temperature, conventional ways is that you will put a couple of thermocouples over here and then try to get what is the temperature distribution, or rather what is the temperature at this particular point wherever the bead is. So here the issue is that you are only getting information at a single point, and then you are also intruding with the system, the physical configuration or the physical phenomena that you are studying. Compared to that, if we make use of these laser based or light based measurements, you can have the same flame. This is a representative interferometric image or movie, and because we are making use of light, they are practically inertia free. It is not intruding with the system, so these are completely non-intrusive measurements, and then at any given instant of time you are getting the whole field information. So what you are doing is, what we are getting is spatio-temporally resolved whole field information, and that too experimentally. So this is what is the primary motivation, and then of course this is one projection movie, and just like they do computerized tomography, if you record projection data from different angles, you can generate the entire three-dimensional distribution. So time resolved as well as space resolved information. These are some of the photographs of the setup that we have developed in-house at the Department of Mechanical Engineering, IIT Bombay. These are some of the interferometry based, gradient based methods, and these are the major equipments that we generally use. And this shows the natural convection example, and this is one of the two-phase boiling heat transfer. These are some of the preliminary representative results, how you convert this two-dimensional information. This is one of the interferograms, and from here you can deduce this whole field temperature distribution, but then this is at one projection angle. So this is a completely path average data, two-dimensional data. But if you have your test apparatus something like this, and you record projection data from different angles, and then you apply the principles of tomography, you can have the section wise images, so you have the entire three-dimensional data. So we applied these techniques for natural convection as well as forced convection, and these are some of the Nusselt number surface plots at the walls of the heated cavity. So you can see the variation, the spatial distribution of how the Nusselt number varies at the walls of the differentially heated cavity. This is one of the applications where one of the passive ways of enhancement of heat transfer, flow through a channel. In conventional channel, plain channel, you will be having the boundary layer that gradually grows. You can see the thickness is relatively small, and at its downstream direction it keeps on growing. So the idea is that in order to enhance, we need to disrupt this thermal boundary layer. So what we did, we basically, it's a standard way of doing it. You insert a cylinder and then the flow interacts with this. You have wake vortices, and we visualized how these wake vortices can be actually captured. The good thing with this approach is that if you want to have the flow velocities, generally you will go for PIV, and then if you want to have temperature distribution, you will go for some thermocouple based measurements. But here with the same technique, we are capturing the wake vortices as well as we are capturing the whole field temperature distribution. From there you can get the local distribution, time resolved distribution of Nusselt number. So it avoids the need of multiple techniques, which makes it even more simpler, more straightforward, and the errors would be on a lower side. We applied the same principle, but here we, instead of a single wavelength, we coupled two wavelengths, 457 nanometer and 632, in order to have the simultaneous measurements of, because your convection may be concentration difference driven or temperature difference driven. So in general it becomes difficult to decouple the effects of these two. So for that we have developed dual wavelength interferometry, and then we have successfully shown the demonstration of how to estimate simultaneously the solutal diffusivity and the thermal diffusivity through these experiments. This is one of the projects which was supported under the Swर्ण Jayanti Fellowship. This is, Anil was talking about nebular dust. He does not like nebular dust, but for us nebular dust is of interest because it has some connection with how the early solar system was formed. Here what we do, and initially it is generally believed that these were all silica particles which were floating, freely floating in space, and because of some phenomena they got turned into molten state, and as soon as the nebular dust strikes these molten spherules, the crystallization happens. Now what people generally do, they make use of furnace based experiments to simulate this entire thing, but furnace based experiments lead to heterogeneous nucleation. Our idea was that if we can somehow levitate these spherules of 2 millimeter diameter and then let them solidify, let us see if we can reproduce the texture. So these are some of the textures that we have reproduced in our lab, and these are some of the textures that have actually been found in some of the natural chondrules. So the idea is can we simulate somehow what were the formation conditions of early solar system. So this is one of the facilities. I think this is the only one in India. It has huge utility. It has complex set of optics, which again has been developed in-house, and then we can also have the whole field temperature distribution and how the temperature effects play a role in these textures that are being reproduced. This is just biomedical diagnostics and therapeutic applications. This is cryosurgery based experiments. Here we have made use of the turbid medium. Generally the light does not go through because of multiple scattering, but then we made use of that phenomena in order to record some meaningful signals. So here here we have a cryo probe, and then it is actually inserted into the turbid medium, which is biogel. And good thing is that you can trace in real time, you can trace the freezing front, and accordingly you can get the temperature distribution as well. So this has immense importance as far as clinical applications is concerned. You can in real time you can do that. And one of the major areas is this two-phase in nucleate boiling. Again, we have made use of what people generally do. They use videography techniques to get the bubble dynamic parameters. But our gradient based, and then they make use of either thermocouples or IR based measurements in order to get the temperature distribution. Our gradient based imaging techniques, we have successfully shown that you can simultaneously record the bubble dynamics as well as the whole field temperature distributions in the context of nucleate boiling. So here you have a single nucleation site. You can see a bubble that is growing, and once you have these images, you can convert them into whole field temperature distribution, and then you can also get this is generally it is done through various mechanistic models like RPI models. We have provided the whole field temperature distribution, and from there you can calculate the different components of various components of heat transfer that are associated with boiling heat transfer, like evaporative heating, superheat layer, contribution, bubble growth, all those kinds of things. So this based on these experiments, we have proposed boiling curve under subcooled conditions. This was an encouraging remark from the editor-in-chief that these results are quite insightful and may be incorporated in future boiling textbooks. So that was something which was encouraging. Here we have emphasized when a bubble grows, it traps a very thin liquid layer, superheated liquid layer, which experimentally is very difficult to resolve. So while it grows, you have about 10 microns, 5 microns, and it has been shown that it contributes quite significantly towards the entire boiling heat transfer. So we have set up some specialized optics in order to get the real-time evolution of these micro layer, how it grows and how it evaporates, and then you can quantify and you can relate it to the bubble dynamics. In flow boiling, and here we basically recently in Langmuir we have published on the coupled thermal and hydrodynamic interaction of adjacently located vapor bubbles. These are in pool boiling configuration, and this one is in the context of flow boiling. Flow boiling, it is more complicated because you have the flow inertia and the micro layer also gets hugely disturbed. So through these experiments, we hope that we have been able to contribute towards, because these are all assessed based on the models, and models are based on various assumptions. They don't take into account such kind of complicated interaction between two adjacently located vapor bubbles. And with these, generally it is said that it is mainly the evaporative component that leads to depletion of the micro layer. But when you have these adjacently located vapor bubbles, the hydrodynamic interaction can also lead to an early departure of the bubble. So these are some of the recognitions. One of the recent articles was highlighted as most downloaded articles. There was an explicit mention from one of the groups, the research group in India first attempted to utilize. So this was an impact that was created. We were the first to, and then some few papers which were highlighted through physics of fluids. Acknowledgement, of course, the institute which has provided the ambience, which actually is the best one can aspire for. IRCC, the committee members, and faculty colleagues and friends at the Department of Mechanical Engineering, IIT Bombay, funding agencies. Importantly, students who have shown readiness to venture into optics-based measurement techniques, untiring and focused efforts, and of course the reviewers. Thank you very much for your patience. Thanks a lot.